would like to take this opportunity to briefly show you INESC Microsistemas e Nanotecnologias, or INESC-MN. So we are a private non-profit research and development institute established in Lisbon, Portugal. And we specialize in world-class research, advanced training, and service providing on micro and nanofabrication and microsystems based on our clean room facilities and laboratories. We have up to 18-inch wafer capability and structure definition with minimum feature size of 30 nanometers. And we focus the majority of our work in strategic areas of ICT, health, Spintronics, thin films, MEMS and biomems, biochips, microfluidics, and device and material simulation. To know more about our activities, I invite you to visit our website at www.inesc-mn.pt or visit us in Lisbon. So without further ado, I give the word to our moderator for today's session, Dr. Carlos Reis from the Materials Simulation Group. So Carlos, go ahead.
Okay, thank you, Vanya. Good afternoon to all of you. Thank you for attending this seminar series. So I'm a researcher here at INESC-MN, and my group focuses on material simulations using methods based in quantum mechanics. So I believe that a deep understanding of quantum mechanics is fundamental to the research and development of novel materials and devices. And topological materials in particular are a very active field of research in condensed matter physics and can potentially yield many interesting technological applications in the future. So I don't know much about this subject, but I thought that it would be interesting to the INESC-MN community if I invited someone with a strong background in this area. And so today's speaker, Dr. Bruno Mera, is a theoretical physicist with a strong inclination toward mathematical aspects. He is a member of the Security and Quantum Information Group at IST, and his research focuses mostly in quantum matter and the study of geometrical and topological structures which capture the underlying physics. Our speaker has published several papers on his research topics in the last few years, including high-impact publications in physical review letters. And I had the pleasure of working with Dr. Bruno Mera when we lectured a course at IST entitled Complements of Condensed Matter Physics. So I invite you to hear our speaker presenting the talk entitled Topologically Protected Quantization of Work. So welcome, Bruno. The floor is yours. You may start when you're ready.
Thank you very much for the kind introduction. So I will begin by sharing my screen. I hope you can see everything. Then I will do this full screen. So as Carlos said, I work in, my research develops in the study of quantum matter. And in particular, I'm very interested in, the interplay between geometry, topology, and response of quantum matter. So, and today I will bring you a recent work. I mean, some of you may say it's not recent because it's from 2019. So, but at the pace at which science develops nowadays, it's not recent. But in any case, I will try to convey that this is an interesting phenomenon, which stems from the topology of the wave functions and from the intricate phenomenology that occurs in quantum mechanics, and the fact that when you define a wave function, the latter is only defined modulo phase. So there are, this might seem a bit non-intuitive because we're not used to thinking in these terms. But again, once we go to smaller and smaller scales, non-intuitive things can happen, okay? But the phenomenon that I'm going to talk about today is actually at the interplay between classical and quantum mechanics. So, okay, without further ado, I will just begin. Okay, so I will begin by giving you a background on quantization of particle transport and talk about the related phenomena, which is not the same actually, but it will be good to keep in mind this phenomenon of it is essentially called Thouless pumping. Okay, and then I will talk about the phenomenon itself, which is the topologically protected quantization of work. Okay, by the way, please feel free to interrupt me. I have a tablet here, so if you want me, I can explain things in good detail. Okay, so one of the most intriguing aspects of quantum physics is that basically certain physical observables have quantized values. For example, quantization of energy, as you might recall, for example, in the case of the harmonic oscillator, where you have phase differences which are quantized. You can also have quantization of linear momentum if your particle lives on a ring, or angular momentum. Then also response coefficients can be quantized, and this quantization, when it happens, might be topologically protected. One of the greatest examples that we know in nature is the quantization of the Hall conductivity. When you have a two-dimensional slab and you have an external magnetic field piercing the sample, then if you fill one Landau level, then the response of the system, the conductivity is quantized to a very good precision, and this quantization is topological in nature. Okay. So now I want to talk about, as I said, the Thouless pumping and the quantization of particle transport. So in 1983, Thouless proposed the idea of a topological charge pump. And what happens is that you have the transport of a charge, which is described by an adiabatically and periodically evolving Hamiltonian, is quantized, and it is determined by a Chern number. So it's good to keep in mind a toy model of this effect. And one can consider a gapped translation invariant family of free-Fermion Hamiltonians in a 1D lattice. So you can see, for example, if you have a one-dimensional lattice and you have a pi-binding model in 1D, and you have and this Hamiltonian is periodically driven, so you have a period T, okay. Then if you do next to leading order Adiabatic approximation, and I'm certain that you know the Adiabatic theorem in quantum mechanics, what you find for the displacement in a period of time of the driving of the center of mass of the fermions is that this is quantized, and the quantization occurs in units of the lattice spacing. And there is a topological invariant that occurs here, which has to do with the Berry curvature in some appropriate sense. Okay, and this is very robust. What do I mean by robust? Well, it means that if you perturb your system by having some perimeter that you vary adiabatically, and if the Hamiltonian is gapped at all times in a continuous fashion, then this C1 that I have here, which is called the Chern number, that it will remain the same, okay? This is a very important ingredient in all these stories, is that you have topological invariants attributed to some band Hamiltonian, and that this topological invariance gives you some notion of robustness. And this is very important if you go to the lab, because you don't want, well, you would like to measure things that are insensitive to certain perturbations, or at least to some mild perturbations. Okay. Okay. So another thing that I want to say is that this Chern number is somehow a measure of the twist of some wave function. In this case, it's the time momentum single particle wave functions of the lowest energy band, okay, or the lowest energy bands below below the gap or below the Fermi level. And if C1, if the first Chern number is different from 0, then it is not possible to choose everywhere non-vanishing wave functions which are periodic in time and momentum. Okay. So perhaps, well, this is just me saying that in this case, what is quantized is the displacement of the center of mass position of the fermions. But concerning this first point here, perhaps it's important that you have in mind what do I mean by the twist of the time momentum wave functions. And because I like to draw, I give you an example here of what I mean by that. Okay, so for a moment, and this is not true in general, suppose that your wave function is real. Okay, and that you have at each time you have to select some wave function. And then you're going to select this wave function in a period t. So the Hamiltonian being periodic means that after t units of time, the system must go back to itself, okay? But in quantum mechanics, the system going back to itself means it goes back to itself modulo a phase, okay? So you have an ambiguity that, that you can explore here. And so if your wave function was real and your space of parameters was a circle, and by the circle, I mean this dashed line here in the base, okay? So over each point on this circle, you're to prescribe a wave function, okay? There are two classes of topologically non-equivalent configurations. So in the real case, okay? So one is in which your wave function, you go around this circle and it comes back to itself. And the other, because well, the wave function better be non-vanishing because you want to prescribe some non-trivial wave function, then you go back, and it might come to the inverse of it, or to the opposite of it. And what you're realizing is that there are two non-trivial configurations. Well, there are two configurations. One is trivial, and it corresponds to the topology of a cylinder, and the other is non-trivial because there is a twist in the wave function, and it goes back not to itself, but to minus itself. And you can think of this as, well, if you try, if you look at this state above and you want to deform it into the state below, you'll find that you cannot do it in a continuous fashion, okay? So by the way, this in mathematics is called the Mobius strip. So there are some fascinating mathematics occurring. And this is a very, actually a very simple example, the most simple example you can imagine. Because here, what we are considering is not one dimension, but two dimensions, and our wave functions are complex, okay? Okay, so I told you all this story, and the title of my talk was Quantization of Work. So you ask yourself the question, is it possible to have quantization of work performed by a force on a particle? Well, in principle, no, not even if the work is performed by a periodically oscillating force. Well, even if we try to consider the average work, averaged over the period of the oscillating force, the answer is still generically no. So there must be something that allows you to have something like this, but certainly not at the classical level, but at the quantum level. So in the following, we'll see how the topological twist of the wave function of an atom in 1+1 dimensions, and here 1+1 dimensions, I mean time plus space, okay, can give rise to quantization of the work performed by a force felt by the atom. This effect, as I said before, is at the boundary between classical and quantum physics, because the twist of the wave function is felt in the classical motion of the atom. So this, by the way, I have to tell that this work was done in collaboration with two authors. One is this fellow Krzysztof Zacha from the University of Krakow, okay? And the other is Yasser Omar, a colleague of ours from INESC. Okay, so let us introduce the model. So consider that you have an atom where the ground state energy level is characterized by total angular momentum F equals to 1. And that you have, therefore, you have three independent states labeled by angular momentum 0, 1, or -1. In the presence of, so if you have no magnetic field, these levels are degenerate in energy. But if I put an external magnetic field, then the sublevels split. And if the atom is subject to two counter-propagating circularly polarized electromagnetic waves of frequency omega, the internal degrees of freedom can be described by the dressed atom Hamiltonian in the rotating wave approximation. Okay. So it looks something like this. I'm sure you're familiar. This is a bracket notation. Okay, so this is just the projector to a given level. Okay. And then you have three quantities here, delta, omega, and omega star. Omega star is the complex conjugate of omega. And very importantly, omega is a complex Rabi frequency, and it depends in position and in time. And this delta quantity is the tuning. Probably some of you have heard this word, which depends only on time. So I'm going to request that this delta of t is oscillating in time with period depth of the modulation of the magnetic field. There are some certain parameters here. And then the Rabi frequency, omega, depends periodically on time and also on space. Okay? So you have a decomposition like this. So you have a period in time, which is important. And you also have a period or a wavelength, if you want, in space. Okay. And so what you find is that this 2x2 matrix, actually 3x3 matrix, is periodic in time and in space. Okay, so you find yourself in a condition that your space of perimeters is topologically a torus, a two-dimensional torus. Okay. So here I'm just saying what are these perimeters, alpha1 of t and alpha2 of t. And they are chosen carefully. Okay, so you want to make an experimental setup where this is possible. And actually, we in Poland we spoke with experimentalists just to be sure that something like this was feasible. So as to have desired properties. Okay. So with these ingredients, we have a dressed atom Hamiltonian, which assumes the following form. So this thing that I wrote here can be written as a linear combination of generators, which I'm going to call J mu. And why am I calling it then J mu? Well, because they will have the same commutation relations as angular momentum generators, okay? And you have three independent parameters, B1, B2, B3, which are periodic in time and space, okay? And for those of you that have seen these two-band Hamiltonians, you'll probably recognize this kind of structure where instead of J mu, you have the Pauli matrices, okay? And then well, this is very similar because J mu form a representation of spin 1 of angular momentum. And if you do the math carefully, the condition for this Hamiltonian to be gapped, and which means that there is a spacing between the lowest energy levels and the first excited level. Okay, is that the norm of this three-dimensional vector composed of these three components is non-vanishing. Okay, so if you denote by B, well, this is what I would say is that there is some space-time periodicity tau, which comes from the magnetic field periodicity in time, and here there is periodicity in space. So you have well, you're instructed to identify positions that differ by this wavelength and times that differ by this period t. And what you find is that you have for each t and each x, you have eigenvectors and eigenvalues, right? And the eigenvalues describe bands in space-time. So probably you're used to seeing bands in momentum space in the Brillouin zone, but here you have bands in space-time, okay? So, and you see, well, maybe it's not completely clear from this picture, but I think it is, that you have a gap separating these three bands, okay? There's actually a flat band lying precisely at the zero energy. And this is for some specific values of the parameters of our theory. Okay, so again, what happens is that locally in position and time, you can find these eigenstates, but if you try to define them globally, you'll find some inconsistencies. Okay, so now what you're going to do is you're going to initiate your state in one of these bands, for example, the lowest energy band, and then you're going to drive the system adiabatically so that you can use some kind of Born-Oppenheimer approximation. And the effective dynamics at the quantum level become the Schrödinger equation coupled to an external synthetic gauge field. And what is the external synthetic gauge field? Well, it is described by the Barry connection associated to this lowest energy band. Okay, so if you do your calculations carefully, when you project out the Schrödinger equation to this lowest energy band, the effective dynamics looks like the Schrödinger equation, but now the Schrödinger equation is coupled to a gauge field. And the gauge field only has to do with the fact that we forget about the bands that are above this band. So the gauge field, you know, gauge fields in nature appear because we have some kind of redundancy in defining the physics. But since here we are projecting out things that existed in the system and we're no longer seeing them, the gauge field is telling you about this ignorance that you have, okay? And this only makes sense if there's a gap, because if the gap is too small or if the gap goes to zero, then even if my dynamics are adiabatic, I am not sure that I will keep my state always in the lowest band. It can jump to the highest bands. Okay. So, by the way, besides the Barry gauge field, there's also a notion which is the Barry curvature, which is simply, if you're familiar with this, well, it would be like the curl of the Barry gauge field. And in this, and because we are in space-time, it will have the interpretation not of a magnetic field, but it will have an interpretation of an electric field force, okay? Now here it is synthetic because really there is no charge, okay? So this gauge field is a U-on gauge field, but there is no charge in the sense of an electric charge, okay? So it will be given by something like that, okay? A1 and A0 are the components of the Barry connection, okay? So perhaps I should write that the Berry connection, well, let me put it here. So you have these dressed states, eta I of t and x, and to compute the Berry connection, you simply make the overlap of this state with the derivative of itself, okay? And this defines you a gauge field, because if you change the phase of the etas, which are allowed to do by quantum mechanics, the gauge field transformed as a gauge field by a derivative, okay? Perhaps you can, well, if you don't understand this, please ask me, I can write it down, okay? So this is the electric, yes, please.
Bruno, maybe you could explain us a little bit more about the Berry curvature, because I don't think that most people are familiar with it, so, including myself.
It's very that's a very good point. I'm going to go to screen 3. Do you see my notebook? Do you see this?
We're seeing it now. Thank you.
Very good. So, so first, Berry connection for starters. So you're having some Hamiltonian, which here is the dressed atom Hamiltonian, which depends on time, and it depends on the position x. Okay, here x is in one dimension, and t is the time variable. And this is periodic in time and periodic in space, with period t and period 1. Okay, and you found some eigenstates of this 3 by 3 matrix, which I denoted eta I of t and x. And these ones correspond to the bands that I described above, right? Eta I of t and x. And you see that this eigenvector equation is not changed if I multiply eta I by a phase. So I am free to relabel these by some space-time dependent phase, phi I. You see, this does not change the equation. And so the Berry connection is essentially, well, let us fix one of these states. I'm going to call I'm going to use the lowest one, and I'm going to denote it just by eta, not to have I everywhere. Okay, so I fix the lowest energy band, and associated to it, I have a gauge field, and I'm going to make it so that it's which you can see as a vector, but it's actually a one form, which is essentially this gradient here. Okay, and here the gradient has two components. It has a component in t and a component in x, right? So one of the things that you see immediately is that once you do a relabeling like that, you see that your connection A is mapped to A prime, which is equal to A plus I gradient of your phase. Okay, so you see that in this is like in electromagnetism, that you have the vector potential, and once you decide to use a different gauge, for example, you can have the symmetric gauge or the Landau gauge or the London gauge, whatever gauge you want. Once you do a different gauge, then you have a transformation like this. And the Berry curvature F, if you want, well, it's actually two form, but I'm going to denote it as a vector because I'm sure that you're more familiar with this, is the curl. You can see it as the curl of A, okay? And so this is vectorial in nature in 3 dimensions. But what happens is that if you have 2 dimensions, this no longer behaves like a vector and the transformations, it actually behaves like a scalar, okay? Why? Because, well, you should see that this thing has to be integrated in an area, okay? And while in 3 dimensions, if you draw a cube, you have 3 types of areas, depending on each of the 3 planes that you can make. In 2 dimensions, you only have 1 plane. And actually here, the plane that you're considering is time and space, okay? So this is a very easy way to see it, okay? Was it clear? Do you need to?
Yeah, I think it was very, very clear, your explanation.
Just one more fundamental thing is that the curl of a gradient is 0. So the Berry curvature is gauge invariant, okay? Good. So let's, I'm going to stop share this part. I'm going back to sharing and I'm sharing my presentation. Okay, and here I put the h bar for convenience, but I usually work in units where h bar is 1. So now one thing that you find is that the work performed by this field on one lattice translation averaged over a period of time is this quantity here. And this is a topological invariant, okay? So perhaps let me, it could be interesting. So how many of you know about the Adiabatic theorem in quantum mechanics? You know about it, right? Okay. So if you know about the Adiabatic theorem in quantum mechanics, you know that if you start the state in a, you know, in some position, in some fixed position or some fixed parameter, and then you change the parameter in time, then the state will carry a phase, which is the Berry phase. The Berry phase has to do with something which is called parallel transport of reconnection. Okay? And what happens is that when you have a compact perimeter space, which is the case like a torus, then you know, you can consider parallel transport along a very small loop in perimeter space, okay? So small that you will reduce it to a point, okay? But then Stokes' theorem will tell you 2 things. Perhaps it's, again, convenient that I go back to my drawing screen. So what you have here is your torus, which is your perimeter space, okay? And I'm going to call it P2. And I'm going to make, I'm going to change my wave function in a small loop here. And what I have by the Adiabatic theorem in quantum mechanics is that my wave function will change only by a phase, which has to do with the parallel transport, I mean, the circulation of this vector here, okay? It's basically the circulation on this loop, which I'm going to call L, of this. I chose my gauge field to be purely imaginary. So this is actually a phase, okay? So if you don't like this, put an I here, okay? That's for convenience. And what happens is that Stokes' theorem will tell you that this is actually equal to the integral on this little surface here, which I'm going to call sigma, of the curl of A, right? Sorry, the sigma, whatever, right? I'm not used to vectorial notation anymore. I'm sorry about this. In any case, what you have, so this is the element of the area. What you have is that you have this identity, right? But you know, since you're in a compact surface, you're doing Stokes' theorem, but you could have chosen equally well the complement surface, just oriented in the other way around, right? This is another possibility. So this would give you, let's call it minus I, the torus minus sigma curl of A d sigma, where it's a volume element of the other side, okay? But notice there is a minus sign because I chose it with the opposite orientation. If you remember your calculus 2 classes, then you see that you have to choose it with the opposite orientation. But now what you see is that if you take this and you put it on the other side of the equation, you find that the integral, well, you have the integral of this plus the integral of that, which gives you the integral on the whole torus, right? You have the integral on the whole torus of the Berry curvature. Well, again, here you put the volume element, okay? The area element, and you find that shrinking this loop to a point, you find that the wave function cannot have changed. So this must be equal to 1. And what does this tell you? Well, this tells you that this should be 2 pi times an integer. Otherwise, it cannot be 1. So what you find is that the integral of the Berry curvature over the whole of your parameter space, which in this case is a compact surface, must be 2 pi times an integer. And this is why the Chern number is quantized. Why is it topologically quantized? Well, for that, I will have to tell you a bit more, but it's a bit outside of the scope. It's not a lecture on that, but it is indeed a topological invariant. Okay, so let me go back to this. I hope this was useful. Okay, so what happens is that this integral here is exactly the integral on the torus, okay? And so therefore it is the Chern number, which has an integer, times this factor here. And what you understand is that this factor here is nothing but the frequency of the driving, okay? So what you find is that the average work performed by the synthetic field on one lattice translation, average over one period of time, is quantized, and the quantization spacing is precisely the frequency of the driving. Okay, so this is quite similar to the effect that I told you before, except that here the roles are a bit different. Before we have the quantization of the center of mass shift in one period of time, and here we have the work done by a synthetic force. Okay, so this is the result. Okay. So if we prepare a state on the positive energy stressed state, strongly localized in position, and you can do this, then the dynamics of the position of the atom, they are approximately described, well, by something that looks like a semi-classical wave, semi-classical equation of motion. But you have to take into account that you have this synthetic force, and also you have an effective potential, which comes from the dispersion of the band. But also you have something which I'm not going to talk about, maybe we can discuss someday, which is the quantum metric, okay? Then you can ask me, well, how can I then extract this topologically protected quantization of work? Well, you can extract the synthetic force from the acceleration of the trajectories corresponding to preparing states localized in different positions at different instances of time. And I don't know how I'm doing on time, but funny story, but I'm going to tell you how does this look like in practice. Well, because when you claim that you have an oval effect, then you should give an experimental proposal. Although I'm not an experimentalist and I'm very far from understanding the full details of this, but I will tell you how I would do it in a Gedanken experiment, okay? So we set some parameters in the theory, which have to do with physical parameters. And then we know that the Chern number in this parameter range is 4, and you can compute it easily from the theory that I had before. If you want, one day I can tell you how to compute this. And then you can draw these trajectories. Well, this is just essentially preparing the state in different positions at different instances of time, letting the dynamics flow, and you get, you know, this kind of plot. Okay? And then this is an acceleration profile. And then for each initial condition, the resulting classical trajectory allows us to calculate the acceleration. And basically, how well you differentiate twice with respect to the trajectory, with respect to time. And then you have the theoretical picture, because you know how these things look like, because your theory predicts your spectrum and your theory predicts your quantum metric. So the point is that to calculate the work, you would need to compute this quantity E, okay? From this, you're computing not E, but you're computing E minus the gradient of the dispersion minus the quantum metric. But then you can cancel out things from the theoretical predictions and try to estimate E. And it would look something like this if you do some kind of interpolation or choose your favorite method. But of course, this requires to have a very good amount of points from your data. Okay. So you see, one of the good things is that the acceleration does not look very different from the electric field itself. It's just a scaling. And the reason is that the quantum metric behaves very similarly to the syntactic field because of some geometric constraints that are involved. Okay, so this is the picture. So there is two contributions that can be obtained by estimating the integral with help of the points presented here in the left panel. Okay, so to end, I'm going to do present this small comparison table between the Thales pumping, which is a phenomenon well known to condensed matter physicists, and this one of work quantization, which I dare to present here. And the difference come in all these parameters. So the first thing is that topologically, the parameter space is the same, is a torus, because if you don't care about the details of what these mean, well, mathematically, they are similar, because they more concretely, they are homeomorphic. So they are a torus. But in terms of physical meaning, in the phenomenon present here, we have space-time, and in the Thales pumping, we have the Bloch momenta, which are the quasi-momenta of electrons or fermions on a lattice or on a crystal. And then you have time. Then you have a gapped Hamiltonian, which in our case is a dressed state atom Hamiltonian. In the Thales pumping, it is a block band Hamiltonian, which depends on time periodically. Here, the wave functions, which I call them by the fancy name sections, but never mind what that means. Here are the dressed states. In the Thales pumping, they are the Bloch states, which you compute in many ways. And I know Carlos computes a lot of Bloch states, from what I understood, by several methods. The gauge field is the Berry gauge field in both cases, except that, again, we are working in different parameter spaces. And in the Thales pumping, it manifests through a coupling to an external field. So, for example, when you measure conductivities, and here it manifests in the form of a field that couples to the semi-classical equations of motion, okay? Which have the interpretation of the synthetic electric field. The field strength, again, is the curl of the Berry field. And the first number, well, the first Chern number has two different physical interpretations. In the Thales pumping, it has to do with the shift of the center of mass of the system in one period of driving. And in the work quantization, it is the average work performed by the synthetic field on the unit cell of space-time lattice, okay? And of course, one other thing that you can say is that here we use the model in which we have the Pauli matrices, but this is just, you can consider models in which these Pauli matrices can be replaced by other things. So, okay, so this is basically it. I hope you enjoy.
Thank you very much, Bruno, for such a nice talk. You were very clear, as always, explaining all these amazingly complex subjects. I would like to invite the viewers to send us some questions so you can address them. So Vanya, do you want to ask a question? Go ahead.
Yes. So in your like, I think first graphic, you had the gaps in between. Do you remember? Yes. So, but my question here is, what is the space that you are considering? Will this occur in vacuum, for example?
Okay, so essentially the kind of system that, well, in this plot you could see it as something. I mean, you're looking here at space-time, right? So your variables are position and time, which are constrained to live in one period. Okay, so if you want to, in a fundamental domain, but they could be for I mean, the theory I developed, we are using here, could be done in the setup of condensed matter, where you have the Bloch momenta of the electrons, and there they are also defined modulo translations of the reciprocal lattice. Okay, so in the particular phenomenon I'm considering here, what you have is an atom that could very well be in the vacuum, but not necessarily, right? So what has to happen is that this atom is constrained to live in one dimension. Okay, so in particular, this happens in the setup of cold atoms in these experiments, where you have this where the atoms are constrained to live in certain dimensions, for example, by adding some kind of potential well that does not allow them to move in other dimensions. Concerning the time itself, that's another question that you could ask. Well, the time here is periodic because simply you're driving the system with a periodic force. Okay, so you end up with some Hamiltonian, which is periodic in space and periodic in time. And when you diagonalize this Hamiltonian, this dressed state atom, because you call it dressed state because the original states of the atom, they are different from these eta i's, right? They call them dressed because they are the eigenstates, right? Like when you dress something, you put an extra structure on it. But yeah, that's, I guess, I hope I answered your question.
Okay, any more questions? Please, Professor João Pedro, unmute yourself.
Hello, Bruno.
Hello.
Thank you for the talk. It reminded me of some concept that I have not used for a while. But you didn't, you know, I know that you are like a theoretical person, but I know that there are some applications envisaged, or at least potential for these topological materials. Can you like just can you point towards them for us? You know, what can you do with these materials?
Sure. So one very important, okay, so this phenomenon here is not oriented towards the particular applications that I'm going to enunciate to you, because they are more familiar, perhaps. But when you have topological insulators, and in general, when you have these topological invariants, so generically, the theory that I presented here usually has to do with the bulk of a material, right? And what happens is that when you go to the lab, you're not just looking at bulk properties, but you can also look at things that happen in the boundaries, right? So you terminate your material to another material, you make an heterostructure, you make you will be interested in these kind of things. And what happens is that this topological perfection has to do with the concept of adiabatic continuity, right? So you want to you have a Hamiltonian that is stable as long as you preserve the gap. Right? But what happens is that if you terminate the system to the vacuum, for example, the vacuum is a trivial insulator, right? So if you terminate your material with the vacuum, what happens is that you cannot adiabatically continue one bulk to the other. And so in order to to put the two things together, you will necessarily have to close the gap. Okay? This is the usual argument that people use to say that if you terminate a topological insulator with a vacuum or with other material, which is trivial from the point of view of topology, then you'll necessarily have states which cross the Fermi level, which violate the gap condition. And these states are very stable. They are zero energy modes, and they are localized at the boundary precisely because it is where you fail to adiabatically continue one material to the other. Okay? And these have applications because it's a resource, right? You know that they're going to be there because topology predicts them, and therefore you could try to explore that for applications. Okay.
Okay, thanks. Okay. That gives me a hint about what you can do.
Sorry.
Okay. Any additional questions, Vanya?
Just a comment on what you said. So you are mentioning topological insulators, but there are other types of materials like maybe superconductors?
Topological insulators and superconductors, yes, indeed. And actually, it's not only that. You can also find similar systems, classical systems, which is quite surprising. Because, for example, when you have Maxwell's equations, if you have some kind of non-trivial medium, you'll find also something which is analog to these energy bands. And there you can find similar topological properties. And there are such things as edge states, which are topologically protected. But I mean, there are people who work on these. For example, Mario Silveirinha from IT also does this kind of things, and it's more focused in electromagnetic phenomena. Okay? So this thing that I said, it's a theoretical framework. So once you have a family of matrices, so you find your favorite system. Okay, you have to diagonalize a matrix which over some perimeter space, which is compact, then, I mean, it's very likely that you're going to end up with the same kind of phenomenology. The interpretation of this parameter space has a role, which is the physical application that you have in mind. But this aspect that I told you, that if you try to put such system in contact with a trivial one, meaning that, for example, a trivial one would mean a constant matrix, okay? A gapped matrix, which is constant, okay? You would find the same kind of phenomenon. You can just play with it in the computer and convince yourself that if you try to put an interface between two such systems, you'll find states which are localized, eigenstates which are localized in the interface. So it's quite powerful.
Okay, any additional questions? I have a couple of questions, Bruno, if you don't mind.
Please do.
Some of them were already asked by the audience, so I won't repeat them. Okay. Do you know something about Spintronics, and do you foresee any role for topological materials in this area?
there are such things as topological insulators, but in which you have the spin plays a role. Okay, so this is something more specific. Okay, so if you want, I can I don't have the details in mind, so that I could try to explain it to you, but I don't want to say something which is wrong. Okay. So I can give you, for example, a review which explores this kind of thing. But I know that there are potential applications to Spintronics. Actually, in my master's, I worked with spin systems, so I'm familiar with the amount of applications and things that are going around there. But yes, the answer is. I'm pretty sure there are loads of applications.
And I also heard that there is some interest in this kind of materials to use in quantum computing. Do you want to comment about that?
So one important thing that I would like to call your attention is that you have so similar arguments from topology can be used in topological superconductors, as Tanya was mentioning. And what happens is that in this case, these zero modes that I told you that appear at the interfaces, they are these exotic Majorana fermions. Why are they exotic? Because they are fermions that they are their own antiparticles. Okay, so in a less fancy language, it tells you that the creation operators for these particles are Hermitian. They are self-adjoint. Okay, but the point here is that you can, when you have these Majorana fermions, they are basically shared non-locally. Okay, so while this is something which is quite non-intuitive at first, but when you start to understand the phenomenon the phenomena that happen here, you realize that this is possible, and Kitaev was the first to realize this. So there are fermions which are shared between non-locally, and they are topologically protected. And once you have these Majorana fermions, you can braid them in some sense. And the braiding operations correspond to some kind of unitary transformations that you make between these particles. And if you have an enough number of these Majorana fermions, and people in the Microsoft labs are trying to, realize these things, you're able to build a quantum computer. But you have to be very careful with these things. Okay, so because you want to have this scalability of quantum computers, meaning that you don't want a quantum computer with 2 qubits or something like this, right? So there are certain limitations which have not been yet, at least to the extent of my knowledge, have not yet been solved, and but it's clearly a relevant area of research. And,
okay, so Bruno, this kind of topological protection could eventually be useful to have this kind of devices functioning at a room temperature, right?
So the subject of room temperature is I studied these kind of things. So one of the things that you have to bear in mind is
Okay, we have some problem with Bruno network connection. We'll just wait a few moments, see if it resumes.
Do you hear me? You
You
hear me now?
Yeah, Bruno, you broke off, so we didn't understand what you were telling us. Could you repeat, please?
Can you hear me? Now.
Yeah, go ahead, Bruno.
Okay. So, this kind of properties, topological properties, is it possible? No? Okay. So these properties, they are usually studied at 0 temperature. All of what I've shown you here is done at 0 temperature. When you turn in the temperature, this becomes an extra parameter. This becomes an extra parameter. Temperature becomes an extra parameter in your theory. And in particular, if the temperature is big enough, you can promote excitations from one band, the lowest band, to the band which comes immediately after. So you have to be very careful with the kind of assertions that you make. And you have to study the topological phase diagram at finite temperature. And you see, what usually happens is that all these at determining temperature, topological phenomena, they are snared out, they are washed away. So it's, I mean, you have to be, you have to cook up something that is there at finite temperatures, which is not easy.
Okay, is there any other questions? No. So I would like to thank our speaker for the wonderful talk that he gave, and I hope that we learned a little bit more about this amazing subject. So thank you, Bruno, for your nice talk.
Thank you for the invitation. Thank you very much. It was very nice.